We've already seen some things with matrices. Specifically, we've seen augmented matrices, and we've seen the coefficient matrix of a system of linear equations, and we've seen how to put these things into row echelon form and reduced row echelon form. But matrices are useful in a lot more ways than just those. So to start talking about matrices, let's make some definitions. So if I have a matrix A, if A is a matrix, Aij is the entry of A in row I and column J. I'll sometimes also write this as Aij, and we also call it the ij entry of A. Sometimes we have a formula or something that will give us each element, each entry of the matrix, and when we do that, we will often write something like A equals Aij. So here, this would be the formula, and the fact that we're using I and J, we just know that I refers to the row number and J refers to the column number. Now a couple of definitions, or a few definitions. An M by N matrix is square if M equals N, if it looks like a square. Bullet there. I should put a little squiggly over here. The diagonal entries are A11, A22, A33, etc. So these are the guys that are in row 1, column 1, row 2, column 2, row 3, column 3, and so on. A diagonal matrix is a square matrix. That square is important. For which all non-diagonal elements, diagonal entries are 0. So there's numbers on the diagonal, but everywhere else it's zeros. So, for example, this matrix here is not square. So in particular, it's not diagonal. This matrix, on the other hand, is square. This is square, but it's not diagonal because this guy and this guy are not 0. This guy here, this is both square and diagonal, so this is diagonal. And that's because this guy and this guy are 0, but this guy here is also diagonal. So even though this guy here is 0, that's all right. I don't care what happens on the diagonal. I don't care what happens at these two spots. All I care about is that these guys are 0. One more type of matrix that I want to define, and that's the scalar matrices. So a scalar matrix, put a little squiggly here. A scalar matrix is a diagonal matrix all of whose diagonal entries are the same. So for instance, the matrix 2, 0, 0, 2 is a scalar matrix because this guy and this guy are the same, and it's diagonal. I also wanted to find the identity matrix. Let me write that so it's a little bit more legible. Identity matrix. That's the matrix I sub n equals 1, 1, 1. So it's the diagonal matrix with ones along the diagonal and zeros everywhere else. So I put these big zeros just to emphasize that there's zeros everywhere else. So for instance, I2 is 1, 0, 0, 1. I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. And in fact, we even have technically an I1, and that's just this guy, 1. Also wanted to mention when the size is implied is kind of obvious from the context. We'll leave off the subscript. The next matrix I want to define is the zero matrix. We will usually write this like O, say 5 by 3 or something. So this is the 5 by 3 matrix with all zeros. So in general, O m by n is the m by n matrix with all zeros. We'll usually and almost always leave off the subscript, and so I'll put this over here. So when the size is obvious from the contents, we'll leave off the subscript. Note this is a capital letter O. So this is a capital letter O. There is no standard notation for the zero matrix. This is the notation the book uses. One final definition. Two matrices A and B are equal if, now let me put a little squiggly under here, they have the same size. So in other words, the same dimensions, the same size. So like the size of a matrix with 5 rows and 3 columns is 5 by 3. Note that's 5 by 3 is one thing. It's not 15, it's 5 by 3. If the same size and all their entries are the same. Their entries are the same. So in particular, the matrix 1, 2, 3 is not the same as the matrix 1, 2, 3. We'll put a little example symbol over here.